So let's start with something very, very simple. We'll do a simple one-parameter model just to get our feet wet in the Bayesian concepts and try to. So generally, one-parameter models are not useless. They are actually can be very useful, especially when we use the one-parameter structure and we add parameters by adding a certain layers of hierarchy later. But those one-parameter models, or in our case, the one-parameter likelihood, will allow us, for example, to capture what is the average difference between something, how strong there's association between two variables, what is dependence of one variable on another, how groups are different from each other, how much. One parameter model can be actually very important, and we'll focus on a very simple model that you should really know from what you've done before, which is the binomial model. Binomial model is a model that, for example, is used to compute how many heads or tails we will be computing, we will be able to flip when doing 10 flips, for example. So it says having n exchangeable trials. So it's not a sequence. Our next experiment does not depend on the previous one. We perform n experiments, and they have two possible outcomes. Usually success and failure. This is something like, for example, classification, right? Classification is a typical situation when we have a binary selection, yes or no, success or failure. The binomial model is a natural likelihood dependent on one parameter, that is the probability of success. And it has a closed form allowing us to compute depending on when y is the integer value, right? So how many successes, the probability of having y successes conditional on theta is given by this formula. And what we need to understand at the moment is that likelihood and probability distribution, the probability distribution of y differs from the likelihood just by understanding what is variable of interest. Because knowing theta, we can easily get a probability distribution describing how many y's there will be. But on the other hand, knowing fixed y, we have a function of theta. And this function of theta gives us the probability of continuous probability of what theta is most likely given and y. So, for example, having 11 trials having 7 successes, we can compute directly the values of probability density function of theta. So, having it analytically, assuming that any kind of theta is possible, so in other words, saying that if we do not know what theta, have any knowledge about theta, we can assume that theta is uniformly distributed on the interval 0 between 1, because this is the probability of success. So look at this. Here we have a likelihood, probability of y given theta. This is the posterior distribution. This is essentially the same formula. The only thing that changes here is what we understand about that. What we assume to be variable and what assume to be parameter. And this thing, that now depending on theta, has a very nice property that such function becomes so-called beta distribution. And this is proportional to the beta distribution. Beta distribution is a distribution of theta with two powers, having that theta times to one power times 1 minus theta to other power. This is beta distribution. This is binomial distribution. Almost the same, just binomial distribution is a distribution of discrete events, distribution on integer numbers dependent on fixed theta. This is a continuous distribution on interval 0, 1 with fixed y. Okay? So in such situation we have the same formula, but it means something else, because something else is fixed and something else is given. And for simplicity, we just did not use prior for theta here. We just assumed that it was uniform, so we didn't know about anything. The bonus of it being a beta distribution, and generally bonus of any kind of computation, that we get some kind of known analytical formula, known and named distribution, is that somebody did a lot of work for us before. So we have formulas for medians, for moments, for confidence intervals, for cumulative distribution functions, stuff like that. Those things are already analytically computed by an army of mathematicians in years gone by. So this is often useful because we can then use those computations analytically. Unfortunately, in practice, we won't be doing much analytical computation, because analytical computation in these cases actually would be the fastest, because it does not require very complicated computation required of sampling, which we'll cover later. So this is a good thing. So we have posterior with a known distribution, so what can we do? Well, the problem is that now we know the probability distribution of theta, knowing number of successes and number of trials. That's great, but now how do we use a distribution to make a decision? Because all information is encoded in the distribution, which actually, knowing the full distribution is a rarity. Usually we will know something about this distribution, but still it's a function or approximation of that function. How to make a decision based on function? No, well, we use some kind of summary statistic that would allow us to give us, that would help somebody to make a decision. So popular choices are mean, median, and mode. Mean is the expected value of the distribution. Median is a value that lies that 50% of probability is on one side, 50% is on the other side. And we need some kind of measure of spread of the distribution. And mode is the maximum of the distribution. We need some kind of method of quantifying the variation, how spread the function is. And we can use standard deviation, which is very popular, especially with something that is normally distributed. On small intervals, it is less efficient, because we can get results that will move us out of that interval. Interquartile range, so how the samples are spread, also how the distribution is spread, and other quantities that can be used. In case of beta distribution, we can, as said, somebody did the work for us, we can compute the mean directly from our data. Because beta distribution with two parameters alpha and beta, in our case, is a beta distribution with parameters y plus 1 and n minus y plus 1. has a formula for the mean and gives us the probability, give us the expected value of theta. Theta, which is the probability of success, right? And this probability of success here is expected to be y plus 1 divided by n plus 2. Why, after observing y successes in n trials, we don't expect theta to be y over n? Shouldn't it be like we had 5 successes, so in 10 trials, so we should have 50% of success, right? Is this an error or is this a feature? Because there's one thing that we should also be aware of. What happens when we have no trials? Because if we would use y over n, we have 0 by 0, right? In this case, by using this distribution, we are encoding in our assumptions there are always 2 possible successes. Those options, right? Either, because if we have 1 trial and no success, so again, what is the probability of success? Is it 0? No, because we know that it is possible. Because we have 2 options. It's a coin flip or something else. This success is possible. So having our knowledge, we start after 1 experiment that it is the probability will start with 1/3. If we will have more trials with no successes, the probability of expected probability of success will fall. But still, there is always the possibility that when 1 success happens, it still is possible having the data before, right? It might be more and more unlikely by having more and more data, but still, such presentations gives us information that our model accounts for a situation that there are 2 possible results, and not having any kind of knowledge about that allows us to have it. But mean is one thing, and it's fun and giggles and everything is okay, but as I mentioned, standard deviation, especially in content interval, might be problematic. Because if there's a large variance and small mean or large mean, it could give us results. Are you okay? Yes. It can give you values, for example, excessive 1 or negative. Interval summaries take a probability distribution function and find the interval for given probability. And typical are central interval, so we have we assume that because assignment of probability interval, because remember, generally, if you remember from your first year of studies, the probability of event that a continuous variable lies in certain interval is the integral of probability density function over that interval, right? And if we are interested, for example, in 94% probability interval, then we need to compute those this interval, so choose this interval in some kind of way. And those intervals are not unique, because if we'll be moving the interval, we can get multiple intervals that have area of 94%. It might be wider, it might be thinner. So there's few options of selecting that interval. First popular is a central symmetric interval, so find a symmetric interval around mean that will have the required probability. That's one thing. The other is highest posterior density region, which is the smallest interval that contains given probability. So it can concentrate in a certain area. And of course, interquartile intervals are the simplest, because you know what are the quartiles and you just get the selection. So if you want to typical interquartiles, so between 25 and 75% quartiles, so you get the around the mean with given probability. Generally, a special case of central interval. So having that, highest density interval is nice, but requires the most computation, because it requires from us having the optimizing the width of the interval, right? So it requires certain analysis of the distribution. In case of analytical computation, it becomes very difficult, because you have to first solve the integral depending on the parameters, and then optimizing those parameters. So might be difficult on two variables optimization and stuff like that. But central intervals are not so fancy if the probability distribution is is smooth model. So in a worst case situation, a symmetric central distribution will give us a very wide interval, including a lot of impossible situations. It's almost like in Poland with in the mean income, right? Nobody earns the mean income. People either earn more or earn less. Very limited number of people earns the actual mean salary in Poland. And it's not symmetrical actually, because there's a giant spike on very low salaries, and then there is a heavy tail on the higher salaries. So there are people that are earning a lot as specialists, but there's also people who earn absolute amounts as CEOs or something like that. So those kind of things that move farther and farther away. So the option is to use disjoint highest density intervals, and just find that this you can find one small interval, but you can, for example, find two that 94% probability will be here and here. So either there will be group here, group here. And this is complicating the reporting of the result, because generally people won't understand that. That's the very big problem, that people do not understand probability at all. They do not understand chances. They have very limited concept of what works and what doesn't work, at least intuitively. When people are educated and stop to think, to decide what is what, and use their own knowledge, they will be fine. But if people are given to intuitively solve a probability problem, they will usually fail. The more complicated problem, the failures will be more common. So, having that, we've described likelihood. We have a model, very simple one at the moment, and let's focus about priors, because at the moment for our first case, we have claimed ignorance. We know nothing. Knowing nothing, in case of binomial distribution, knowing nothing is a uniform distribution. all values of theta between 0 and 1 are equally likely. Uniform distribution is not always absolute ignorance, because for certain parameters in their interpretation that will not be enough. For example, if it is very good for finding what is the mean of something, so for the location parameter, where is the bulk of probability located, then the mean is, the uniform is relatively okay to find ignorance. In case, however, of spread of variable, if we are fully ignorant about the spread, then we should also be aware that spreads of orders of magnitudes are equally likely. Not knowing about anything, we do not know that the variance is like 10% or 10,000%. So in that case, assignment timing ignorance might be limited. Either way, priors have two generally. Our prior knowledge about something has two interpretations. One is more basic and more easy to understand in certain aspect of quantify, that when there are multiple possible thetas, for example, when we are investigating coins, are they fake or real, let's say. So there is this big population of possible coins, right? Minted and different kinds of coin and cheated coins and stuff like that. So there is this big population of coins. So our prior knowledge gives us the quantification of those coins. So what we know about the existing population of coins that we can use to our experiments. This is the population interpretation, that theta is just one realization of the population that is away. The second one is our state of knowledge. And state of knowledge is more general in a way, because we can assign it to something that haven't happened yet or happened in very limited situations. So for example, as I mentioned last time, probability of an accident by a new driver, and this new driver. So we have some kind of intuitive conception or some kind of determined conceptions, what knowing about it is we can use. And so we know that it's uncertain, we can say what kind of uncertainty it is, but it is not necessarily repeatable situation that can happen multiple times. This is a philosophical thing, but just to understand what kind of happening we have here, what kind of prior understanding. And we will have a separate lecture on priors, but for today, we need to understand there are three types of priors. Mainly three types of priors. Others can be given into those. First ones are non-informative priors. Non-informative priors is stating complete ignorance about the subject. Weakly informative priors are stating some but very limited information about the subject. And finally, informative priors, we know, and because we know, we can use that knowledge. Non-informative priors are, let's say 10, 15 years ago, were still an important thing. Now they are not. This was still a residual of these frequentist Bayesian wars, when people wanted to be fully objective as possible, so they wanted to know how to quantify the fact that they don't know. That is why it was determined what kind of priors maximizes entropy, so it does not provide any information besides this information you have, and stuff like that. There's a little practical use for non-informative priors, and they are not even being used as defaults in software. So usually there are some kind of priors. Generally, their place was taken by weakly informative priors, because non-informative priors, really, the only thing they made was made computation difficult. Because it gave you unbounded space of parameters to explore. And in not fun situations, it could happen that we would go to places where no one has gone before, and our software would collapse because it wouldn't be able to return from that. And so the generally idea is to use weakly informative prior as a tool for some kind of regularization, to put some kind of soft bounds of where our solution should be. They are soft, so they can be left. So even if the data supports it, we can move away, but still we are not allowing completely unbounded exploration. So generally, weakly informative prior is used for giving models some leeway, but not too much. And if software uses defaults, usually weakly informative priors are defaults, and there are multiple types of weakly informative prior depending on stuff. And you can reach them in two ways. One way is to get the non-informative prior unlimited a bit. So, for example, instead of using uniform prior, let's use normal prior, but with 100 of standard deviation. So it will be very wide. It generally would give you possibilities of values between minus plus 300, and in case of small parameters, relatively small, it stays where it should stay. So we have possible spreads, but still it's not too much. So depending, of course, on the case, weakly informative priors can have much more smaller scales, because the other way of getting them is that you know something, but you don't want to use that knowledge in full extent to force your model to your previous preconceptions. So you know that, for example, the relationship between two variables should be positive. Because, for example, the more items we sell, the more money we earn. So there should be a positive relationship. So you can use prior that keeps it on the positivity, but because you know that, but still you can compensate for. You can give a lot of leeway how positive it is. You know that it, but like you don't say that okay, it's 1.7. If we assign normal distribution with mean 1.7 and standard deviation of 0.1, we get a very small narrow window where the parameter can move. Okay, that would be an informative prior. They introduce some kind of information and can express both constraints in a weak or strong way. So getting them in such situation allows us allows us to inject information to our model. And again, it can be good, it can be bad. Because if our model is if we introduce too much prior knowledge, our model will have problem to confront it with new data. Because in case of our binomial example, the very simple way of introducing prior knowledge is especially in this population interpretation. Because if we use beta distribution as a probability distribution for theta, we have a very nice option, with a few nice options. First of all, beta distribution can be also interpreted as a special case of beta distribution is a uniform distribution. Because when we have exactly 0 successes and 0 failures, it becomes a uniform distribution on the interval 0.1. However, depending on number of prior successes and prior failures, we will encode the information in our model. So we can assign a beta distribution that represents our previous experience in this population representation. So we have an actual population of experiments that we can infer about the values of theta, and we can confront it with new data. And that allows us to create this informative prior, and in this case it is very nice because this posterior again has a closed form of a known distribution, and this is beta distribution. This is a very convenient situation. That's why we're talking about it, because it's easy. Harder stuff doesn't admit formulas. But because the creation of posterior, at least the numerator of the posterior, is just a multiplication of the likelihood function and the prior function with, in the same way, during this multiplication, reinterpreting the binomial distribution into beta distribution, because now we are looking at different variables. Then we can group those thetas and 1 minus thetas together, and we get a new beta distribution with two new coefficients, alpha plus y and beta plus n minus y. This is again very convenient because we get the probability distribution of we can compute means and stuff like that because those were already computed by us. And in this case, look that this represents as information of what our experiment contributes to our knowledge about theta. Because our expectation, our mean of our distribution, will always lie between y divided by n and alpha divided by alpha plus beta. So it will be somewhere between of mean of just likelihood and the mean of the mean of the prior distribution. If we have no successes and no trials, it becomes the mean of prior. If we have no previous trials and successes, then alpha and beta become 1, and we get the previous distribution. So, and this is generally everything. This always happens in base statistics. We have our data has to be coordinated together with our previous knowledge. Depending on what kind of priors we use, this compromise might be more or less difficult, but this will be covered later. This case, however, which we had here, it is a very special case because, again, by multiplication, we got, again, by multiplying prior and posterior, we still got a nice distribution. This is not an accident, this is something called conjugacy. Conjugacy is a property with, again, more and more limited application, but still you should know what's happened here, is that for certain likelihoods, there exist priors that when multiplying and reinterpreting likelihood again as part of the posterior, you get some kind of distribution because somebody already computed before. That's a generally assumption. Usually it's that the posterior and prior should be in the same class. So we can reinterpret what kind of change of parameters in prior happened after changing the posterior. So it makes a lot of things easier because generally allows us to obtain a closed form of probability distribution, and that allows us to use either numbers, formulas that are already computed, or at least random number generators created for that distribution before. So because someone knows that distribution, you could create it random number generator. But besides simple cases, it's not that fun. Because, for example, the best case is for multivariate normal distribution. The conjugate prior is something called inverse Weishart distribution. Inverse Weishart distribution is generally horrible. It's the fact that we get formula in the closed form does not compensate the fact that we really do not have a possibility of putting useful information into that conjugate prior. Because conjugate prior has its own parameters. And if they are not interpretable, you need to some kind numerically assign your prior knowledge to that prior, and that becomes more and more difficult. So conjugacy is nice when it happens, because some stuff gets really easier. This is especially important for normal distributions, because normal distributions are conjugating each other. So normal likelihood with normal priors, it's still a normal distribution. And this is very useful because normal distributions are generally useful. So all the fun reduces to computing some kind of matrices. And that's easy, even in multivariate case. However, in all other cases, it's more and more difficult to handle. Okay, so let's have an example from biology. There is a special case in OBGYN, which is called placenta previa. Placenta previa is a situation of during birth that when child is being born, instead of getting born normally by head directly, first things that goes away is the placenta. Placenta is this part here, which usually should be somewhere here, and this is the thing that is connected to the cervix, to the baby, so we can feed from the organism of the mother. And generally, placenta previa is a medical condition during childbirth that well, happens. It happens. And the question was the following. We've observed that, it was observed that during a study of 980 births with placenta previa, 437 of them were female. And the question was, is the probability of girl being born with placenta previa is lower than the generally probability of girl being born? So, are those things related or not? And if we look at it without any context, we just use our beta, because this is again binomial distribution, right? In 980 trials, we had 437 successes, so we want to know, and we want to analyze what is the probability of success from that, and compare it with 0.485. And of course, when we do that without any context, without any consideration generally of what we know before, assuming that we know nothing, it is clear. The 94% probability intervals locates us below that. So from this information, we see that the probability of placenta previa is less likely with girls. But we can actually use our freshly known property of conjugacy to analyze it in more context. So, assuming that we think that the population, the probability is us, the probability of the birth is the same as the birth of the girl, we can assign a beta distribution and see how the data changes stuff. So we will try to incorporate the idea that the proportion of children births is 0.45, at least its mean is, and we will try to use it using conjugate prior, that is beta distribution. And this is relatively simple just by certain coefficient manipulation, because we have beta with coefficient alpha plus beta, and we can, assuming that it has fixed mean and fixed population size, we can solve it for alpha and beta, right? These are two equations, one of them linear, so with a bit of luck you would be able to solve it, right? So we will do computation of the highest density intervals, keeping the mean fixed at the normal population child base, so the 0.485 for girls, but increasing the population. So generally, assuming that already happened before births with this number of events. And if our sample of prior information grows, then we move away from the data. Because posterior median is moving from the one related to the data for small populations to the larger population, moves almost completely back to the median of beta distribution of prior. Moreover, the uncertainty is being reduced because we are generally pumping the model with more data. We had around 1,000 births, we added 10,000 prior births, and it's kept us here. So highly informative prior based on 10,000 experiments before moved us away from the data. And we can see that movement by as long as starting with small population, our posterior is very wide, right? And the mean of the prior is here, the mean of sample is still here in all those cases. So for small initial data, the posterior just reduces to this value here. If the prior population rises, then prior is more relevant and our maximum of posterior moves away from the data, from the mean of the data. Finally, we have a lot of data. Then, first of all, our prior becomes very narrow, so generally assigns around 0 probability here. So our posterior is being drawn here because only there it can do something. Otherwise, it's being cancelled by the because remember that this looks kind of like normal distribution, right? And normal distribution has 3 sigma and like it's less than 1%. So moving away from that, we get the 0. And actually, we don't even need to compute the beta distribution for high samples because then we can just use formulas for normal approximation and use computed standard deviation, computed alpha to get a normal distribution, which is much easier to sample. And beta distribution for population 1000 is undistinguishable from a normal distribution with the same mean and just recomputed standard deviation. So we can use this, and the posterior computation will be the same. But this is not possible to do analytically. Well, it is, but it will be hard. Well, it might not be. Just the computation will be very difficult because you have to use the complicated stuff with error function and spatial functions. So this is the conjugacy. Conjugacy is nice, but in practice it doesn't happen. And those plots are nice, as I said, but again, we need numbers. We need some kind of functions. And for that, we generally need to compute expectations. Because our goal in any kind of computation in statistics is to compute some expected value of something. And it might be surprising for you, but all those statistics you know can be reformulated as certain expectations. Histogram is an combination of expected values in intervals. The median is expected value of certain indicator functions. Quantiles are the indicator values of certain functions. So expected probability of an event is an expected value of an indicator function. So we'll cover that a bit in a few lectures when we do more about computation. But generally, we need to compute expectation of certain functions. And for that, we have to find a way to do it. If we have an analytical formula, somebody computes it for us. In most cases, we have to do something somewhere else. And just to avoid general misunderstanding, no, you cannot compute it from definition using integration of probability distribution. Because expected value, if you remember, is an integral of x time probability of x dx, right? There was something like that. Usually, in one dimension, it can be computed. In any other kind of number of dimension, it cannot. It will just be a horrible, horrible nightmare of computation that takes ages and gives you no close to results. But we'll cover that later. The main point which is here is that we want to compute on certain probabilistic space Q the expected value of function f of Q small. The small q is our variable, which belongs to probability space Q. And this expectation is defined in continuous case as integral, and in discrete case it is a sum, which can or might not be on finite set, because Q might be only countable. And fortunately, we can rather well approximate the expectations using samples. So, if we assume that we can generate samples from a probability function we want, so in this case probability distribution pi, and this set of samples behave like this, that the average of those samples, actually function of those samples, average of function values of those samples asymptotically converges to the expectation, then we have an exact sampling procedure. So generally, if, this is a big if we can sample from a distribution, we can compute everything. And what even is nice that we can quantify the error of this distribution because it's normal, approximately normal. We can, these are the Monte Carlo methods. Monte Carlo from the country in France where there is a lot of casinos. Monte Carlo method was devised in Los Alamos to compute, for computation regarding atomic bomb. It's one of the contributions of computation. Generally, it is a very good tool for computing difficult stuff. And in our case, it's an only tool to generate samples from distributions and compute something with that. That's why Bayesian methods were not practically used until the development of computers, and advanced computers by that, because it was not possible to compute anything analytically or numerically using quadrature or something like that, until we were able to create randomization. And this randomization doesn't solve the problem, which we'll cover later, that the fact that we can generate samples from a probability distribution is a big if, because it very depends on the distribution, and nothing is absolutely guaranteed, because there are issues. Either way, if we can sample from a probability distribution, we can even quantify our error. This is great. So, how to generate sample? As I said, we'll talk about it later, but we'll do a very, very simple case. Like a simple generic case. That we have a generic case of one-dimensional distribution, so we'll stay with the world of binomials, but we'll do a different example. Who played Mass Effect? There's a Mass Effect trilogy. If you haven't played, it's one of the best video games ever. At least it's on multiple discs besides Metal Gear Solid, but Mass Effect is fine. Mass Effect is fine. And from Mass Effect 2, there was a probing mission that you fly to a planet, you drop a probe, and you find minerals. We'll focus on more simple aspects, searching for water on the planet. So we are in orbit. The planet has a very thick atmosphere, so we cannot see anything through it. What we want to know is there water on the surface, and how much of water on the surface is. So we'll drop a probe from the orbit, and it will register, because the planet spins, we spin around it, and we can assume randomly that we'll drop on a random point on the planet, especially that we don't know how the atmosphere moves. So there will be some changes in the trajectory. So we are randomly sampling the surface of the planet to estimate how much water there is. And this is, of course, a binomial distribution. We randomly sample something with a binary result, water or no water, right? And we will use the grid approximation of the posterior. So we will try to reformulate our posterior distribution in a way that is easy to sample. So the main idea is that having our set of possible parameters, in this case theta, between 0 and 1, we define a grid on the 0-1 interval. This grid is usually uniform, so we have the sample, we divided our interval to parts. Then we compute our prior on a grid, because we have a prior of theta having to because of, for example, previous information. Then we compute the likelihood using our data. For given number of value of theta, we compute the value of likelihood. So we add it to the appropriate power of y or n minus y. Then we multiply the prior and the likelihood. And this is the case that I mentioned before. This is the difference between probability distribution, the posterior probability distribution, and the numerator of probability distribution. Because the denominator, in general case, cannot be computed. Because we would have to compute it for all possible values of theta. So, in this case, we just assume that our distribution is defined only in finite number of points, and because of that, we can sum all those values and divide all values of our grid by that, so we can standardize it. And that makes that the sum of all those values standardized will sum up to 1. And that makes it a probability distribution. And depending on the grid, it will look like this. So if we have 5 points, it will be a coarse grid. If we have more points, it will be a finer grid. So we will be able to, we get a probability distribution that is defined on our interval. What is important here, that we are now not working with continuous distributions anymore. We transform the continuous probability distribution function that we couldn't compute exactly because we didn't know how to compute the denominator in general case. We reformulate it into approximate with a discrete probability function. So it has only finite number of points, like in 20-point grid it will be 20 points. And those 20 points have assigned probabilities now, which are equal to value of probability density function of prior times the value of likelihood divided by sum of all those values. So it becomes a nice proper probability mass function. For discrete distribution, we get probability mass functions. And sampling from purely discrete probability is very simple. Because generally, for example, you can use a function in Python called choice that you can sample with replacement from a vector of numbers with assigned probabilities to them. So in this case, we have a vector of numbers, and we've assigned each of them probability, which they sum together up to 1, so we can sample from them. And in this case, we can generate a lot of samples. In this case, the 10,000 samples. So, having 10,000 samples, we can now perform some computation on that. And we do this computation just analyzing those samples. Because there's a lot of them, the error will be small. And they're of course depending on the quality of sampling, but this is something for future. And generally, we can compute means, medians, histograms, probability of events. So we can get what kind of value of theta is here. I've used much finer grid, so it had 1,000 points between 0 and 1 to sample, but so the histogram is much coarser. Jeszcze 10 minut. So either way, we can sample from this distribution and compute those statistics. But that's not all the benefits generally of sampling approaches. Because, of course, in the one-dimensional case, we can plot everything and we can analyze issues. So, for example, we can play with different priors. For example, we can get a prior that having something below 50% is not possible. We haven't met a planet with so little water. So it has to have at least 50% water, and it's not possible to have it less, so we have assigned this kind of probability. This kind of prior is horrible for normal computation, but here with grid it's like, it's a non-issue. And of course we can compute this grid approximation, we can compute this grid approximation and we can see how it looks like. The probability here is drastically lower. In case of different probabilities, I think it's no, here it should be 0. This is something that was wrong, which I haven't copied the right line of code enough, so things happen. This is from this one. If we assign this kind of probability distribution, so a probability distribution that it's more likely that this is around half, but there is some spread here, then it will be some kind of asymmetric distribution and work like this. And this gives us a question how to choose priors. And we are not covering full priors yet, it will be doing in 2 weeks, but generally, expert knowledge is always good. If we have someone to support us, then we can make an informed choice what the prior distribution should be. And this is a very good situation. Generally, defaults or references that you can find in books are bad. For first approximation, okay, but generally based on defaults, you should at least be aware what the defaults were. So just don't try to use something, okay, you did this here, you just should at least know what it was and what was selected. However, what is really helpful for us is simulation. And this is connected to the concept of prior predictive distribution. Because prior predictive distribution is a distribution of what kind of y's, so outputs we can expect, having only specified the model and having only computed and assigned only the prior. So no measurements happened yet. What kind of outputs we can expect? This is especially relevant when we have a multidimensional distribution, because in multidimensional distribution you cannot plot it. In one-dimensional distribution you can plot it and you can see what's going on. If you have 20 parameters, it is not possible to visualize it in a way that be in any way meaningful. So, what can we do? We can marginalize. So we can have a joint distribution of y and theta. And joint probability of distribution of y and theta is actually very available because this is the numerator of our probability distribution, right? It has both y's and thetas. And the multiplication of probability of theta times the probability of y given theta is the joint probability of y and theta. So, we can marginalize this probability distribution. And of course, formally, it's just integrating the parameters out. So we sum or integrate over all possible values of theta, which is of course impossible because theta, for example, is a 20-dimensional vector. And we can't do that. But in practice, marginalization is sampling from the joint probability distribution and then compute using only samples that we are interested in. So if we have 20-dimensional, in this case 21-dimensional vector, y's and vector of thetas, we just keep the y and we look at the y. And it will be the marginal distribution of y. So we get samples from the marginal distribution of y. And what is funny, it is much easier to sample the joint distribution of 21 parameters than to compute the probability distribution, analytically probability distribution of y, and sample from that. So it's easier because generally those things can be done by tree during the inference or during testing of your model. Either way, the idea is that you sample values of theta. Let's say, returning to our case, we take our probability distribution, which is 0 on the first half and 1 on the second half, and we just sample the value. Okay? And because of that, we get a number between 0, 5, and 1, right? We then take that number and we sample from our distribution. We perform the sequence of tests with this probability. So in case of binomial, we like 12 probes on a simulated planet, and we get the y, the number of successes, right? Then again, new sample from prior, new sample from y, new sample from prior, new sample from y. This is how you create a prior predictive distribution, because you predict what kind of values of y are implied by your prior. So, for example, if prior predictive distribution gives you nonsense, for example, values that are not supported by laws of physics, then probably your prior is wrong. This is a very good tool to verify the assumptions about your priors. And it can get more complicated. And it is not the way that we want to generate something that is equal to our data. We are not sampling and checking, okay, this looks like our data is okay. No, we just looked at something that is reasonable. That's something that can happen in this spread. For example, confronted with expert knowledge. What kind of ranges of values we can expect during actual work. And then having that, we can sample from that and get some information. And we can, for example, choose parameters of our prior in a way that will be safer. And depending on our prior distribution, we can select both these parameters or even shape depending on what happens. So using this prior gives us a rather balanced output, which again might be okay, might be not, but gives us possibility of both the genetics ones and zeros. This one certainly will always favor the ones, not zeros. So this is where we can select priors. But how can we evaluate our entire model? So in the context of the posterior, because what happens when we feed it with data? And again, we can use expert knowledge, so we can see how our results are given. And for the expert, the problem always will be confronting the parameters with reality. The expert that is not expert modeler, but expert in the process, knows the values, the measurements. They don't know the mechanism, especially that if you devise the model, right? So you need to give them some kind of data to look at. Is it consistent with something that can be obtained? And this again gives us the option of posterior simulation, which we can compare with holdout data, or we can compare it with actual data. So this is actually an important thing. Does our prior distribution, posterior distribution, generates data that looks like the data that we've already seen? If the data that we've already seen and used to train the model are completely incompatible with our model, then our model is wrong. And we need to reevaluate it and change what is going on. Because if samples from model, from the posterior, are not consistent with reality, this is not a good posterior. And this...
Is the holdout data set similar to, let's say, the test data set in machine learning?
Yes, but the main problem, as I mentioned last time, statistical modeling is especially relevant when you have a little data. And when you have little data, then you don't have the comfort of creating a test set. That's the problem, because if you remove some data, you will have less information for your model to work. So you have to use some kind of generalization methods to handle that and use the data that's available because it might be relevant. For example, it represents the unique case. If you remove it, then it won't help anything. It's called holdout data set because, again, too much word of test is becoming more and more difficult. But it's usually not being used. You usually do not hold the data, but sometimes can happen. Either way, to compare data with something, you use posterior predictive distribution, which is very similar to the prior predictive distribution. Again, formally, is integrating out thetas from the posterior, but in practice, the only thing that changes is that you need to add an additional layer on your model. You have a model that is samples from the posterior, samples thetas from the posterior, conditional on y. So your model is able to generate a number of samples of theta, which you need, for example, for some kind of summaries. You can use each of those thetas to sample from new binomial distribution, for example, and generate new data. And get posterior predictive distribution that we can evaluate and we can work on to get some kind of analysis. So we can use metrics on that, and this is another thing, that you can simulate the outputs from your model, and then you can use some kind of metric on those simulated outputs. For example, a utility function. So if it is the number of successes, then you can compute the monetary gain from that. So you can transform this split of successes and failures into numbers, and then you get the distribution of those numbers. For example, profits, and you get a distribution of profits, and then you can evaluate. And so that's why prior predictive distribution and posterior predictive distribution are extremely important tools that allows you to evaluate your model during creation from the priors and post inference to verify if the model works or not, and after that you can use it to predict either on new populations, or you can predict it on or you can predict utility functions and stuff like that. Any questions? Okay, so thank you very much.